Welcome, welcome, welcome. On behalf of Machine Solutions and BW-TEC, welcome to our showroom and lab here in Switzerland, where we exhibit most of the standard equipment of all brands of Machine Solutions for our customers to see, test, and also use the lab for development work. It's cold outside here in Switzerland, but we are in here excited about the topic of today's webinar, where we speak about rapid heating blocks, which helps us to accelerate the balloon forming process. Make the most out of your BW-TEC equipment. That's the topic for today. So it's my pleasure to introduce the panelists for today's webinar. Right next to me, Timon Chernoch, he's the R&D engineer. He's the lead engineer when it comes to the rapid heating block project. He holds a degree in mechanical engineering and process engineering of the ETH University here in Switzerland, and he will do the most of the presentation today. Josiah Pontley, he's the executive director of BW-TEC here in Switzerland, and as a side note, he's not my twin brother, as some of you asked me before if that's the case. But we are good friends, and so it's a pleasure to welcome you as well here in the studio or in the lab that we have here today. So let me give you a brief preview of the content of the webinar for today. We have 3 blocks. In the first block, we'll speak about the heating block, the new rapid heating block concept, and the benefits for customers that you can reduce your heat up time by 50%, which has an influence on your process time overall. The second block that we will have, the topic there will also be about the heating block, but more about the temperature distribution and the uniformity of the heating block, which will cause a huge increase in the quality of your balloon. Then we will have a Q&A session. We would love to answer your questions, so please type your questions into the chat box and we will answer them in the Q&A session. And then the last block, the third block, is centered about the topic of automation. And we're gonna present 2 equipments to you, BW-TEC automated equipment. One we already have on our website. We're going to demonstrate it, and at the end of the session, we will use that webinar to present and reveal the first time to our audience our new automated machine. So stay until the end. It's going to be amazing. Josiah, why did we do the rapid heating block concept, and what's the benefit for the customers?
Yeah, I think we have to do a little bit of a history talk in order to explain. As most of you know, the PTCA balloon has been developed here in Switzerland by Dr. Andreas Krünzig many years ago. And his first balloons he made in spaghetti pot, right, in hot water. And that's how eventually we started years later building machines for that application. And sure enough, build machines where we used a 3-part mold, putting them into hot water and blowing a balloon. So that was basically our traditional approach of making balloons, of offering machines to make balloons. And that's basically where we came from. It was easy and efficient, but sure enough, it had some limits. And the most important limit was the 96 degrees Celsius, which is boiling water. And so over the years, customers approached us with specific needs that they wanted to create a reliable kind of dry molding process. And that's how we kind of got into the technology, how we offer it today. And most of our dimensions have been kind of defined by our customers, by the URS documents they handed over to us. And so that's how we kind of developed a huge variety of different heating blocks with different diameters, different lengths, and then sure enough also different toolings for all those different balloons that have been produced in the market over the last 20+ years. And sure enough, we over the years we improved our heating blocks, and we also improved the cooling of our heating blocks. We've done improvements in regard to heat transfer and stability, etc., etc. We added barcodes to it and made the whole package much better to use. But interesting enough, we never really got challenged on the cycle time. And over the recent time, this has changed, and we got challenged by obvious reason. And so we decided to do a deep dive, analyze our system, and find improvements in our systems. And so that's why we today can present you our newest results and our new generation of rapid heating blocks and improved tooling design. And so, Timon, if I may hand it over to you, what have we done wrong in the last 20 years?
Let's stay positive. So we have, as Josiah said, we made a deep dive into the existing technology. Most of you, I think, are very familiar with the traditional balloon forming process on machines like 2130 or 1800 machines. BW-TEC is building now for quite a while. And I'll just start going through the process. So typically you start a process, you're applying pressure to your balloon from the inside. You start heating up the heating block. These are just kind of a few of examples of heating blocks we are providing for you. And here you can see balloon molds. So we start up heating up the whole system to typically, let's say, 70, 80, 60 degrees. And everything is getting hot. And we have to wait until the raw tubing or the parison is actually heated up. And it's important for me to point out that during this first heat up, we have quite a delay between what we see from the heating system and what the parison here inside is actually experiencing. So we have to wait until we have reached 70 degrees, and then we stretch, form the balloon, and after that point in time, the balloon has actually quite good contact to the balloon mold. So the temperature of the balloon is following the temperature of the system around it quite closely. We enter into the stabilization phase. If enough time is gone, we're going to cool the whole system as fast as possible. So if we want to improve now this process, we have some limitations because we cannot cut off that stabilization time. This will affect your burst pressure in a bad way. So we have left like these three parts. So the initial heat up, the second heat up to the stabilization temperature, and the cooling. And as you can see now on this graph, I mean, this is kind of the biggest one, the longest time usually. So we also focused on that part in our investigations. Now, our aim was to optimize your existing system. So we want to change the least possible, right? So we actually looked mainly on the heating block itself. This is now a conceptual drawing of a heating block. We do have the parison here inside in the balloon mold. We have the cones on the left, on the right-hand side, and this three-part mold is sitting in the heating jacket of the heating block. Now you can do several different diameters, several different lengths inside the same heating block, so it's actually a highly modular system you're providing. And so the molds are heated by the heating jacket, and when we cool, we do it over this cooling cap over here. And so let's see now how the heat is actually flowing during the process. So we actually have heating cartridges inside of this heating jacket. So we're generating heat on the outside of the balloon mold. And then the heat is transferred from the heating jacket to the balloon mold, from the mold to the cone, and also from the mold and the cone to the air. So here inside, it's the remaining air. And the air is actually transferring the heat to the parison, and it's heating up the polymer. We also have some losses. We can't avoid that, unfortunately. We do have losses mainly to the isolations, keeping the heating jacket in place and keeping the cones in place. So we looked at many optimizations, and what we actually came up with, we changed the material of the heating jacket into another material with even better heat conducting properties. Then we also tweaked a little bit the design. We made quite a an effort to improve the heating cartridges in terms of power. The initial heating cartridges we're using, I mean, we after 10 years also our suppliers made a huge improvement of what they actually can provide. So we are able today to use much more power than we could before, and we also optimized the power distribution inside the cartridge, so you can actually play with where do I insert how much energy. So we worked on that one as well. And one very big point which came also up recently is we played with mold material, because traditionally we didn't really do a lot of mold making for our customers. Recently this took up quite a bit, so we also invested some time in looking for an improved material. And in the end, we also optimized the process, and optimizing the process is one of the biggest points for sure is P&ID tuning. Let me show you our work and results of a 3x15mm PA12 balloon. We have like 3 demo products we like to share our customers, and this is one of them. So we took Parison and inserted a very thin thermal element. So this has a thickness of below 0.5 millimeters, and we placed it in the center of the Parison. And then we went into this first heat up. So here you can see a graph where we have time on the x-axis and the temperature on the y. So we want to heat up to 70 degrees. The dashed line is actually the temperature of the heating system itself, which is reaching 70 degrees quite fast. Now you see that the Parison is actually lagging behind quite a bit. That's what we have seen in the theoretical drawing before. So we made a lot of experiments in this kind of setting and analyzed the data. We looked at when does the temperature is seeing a difference, so the ETEC time. We look at the point where it actually reaches the desired set point value. Is there maybe an overshoot, and how big is it? And then we came up actually with another temperature which tends to be quite significant. We looked at the time where 60 degrees were reached, so 10 degrees below the 70 degrees. And this is mainly because we have seen that the process optimization, P&ID tuning, and so on is mainly kicking in over here. So if we only look at the time at 60 degrees is reached, we could easily compare different heating cartridges, different materials, different mold materials. So this became one of our key indicators of how the system itself, without process optimization, is actually performing. And these are the results. So I'm not going to every detail on this graph. We're actually providing a white paper where you can read like all the details and all the measures we have done. But let's start on the left-hand side. So this is our traditional system with the traditional heating block, traditional mold material, and the heat up is actually the same graph as before. It's looking like this. Now we have used our optimized heating block, our optimized mold material, and optimized the process, and we came up with a reduction of 50% in terms of reaching 70 degrees. So the old one is the blue line, the red one is the new one, and you really see that we really have a big impact on how fast the Parison is getting hotter in this first part of the process. Now, this is only the first part of the process. We do have the second heat up and also the cooling, which also plays into role. And to verify that one, we actually approached 2 customers to be able to get a solid feedback on the performance on that system, which is high.
Yeah, so we were able to reach out to a few customers, and one of them is a good friend of ours from Galway, Ireland, Ray Blowick. His company is called Richback, and he did a test on our improved system. And as you can see now here in the chart, the time really came down dramatically. Like if you see it here on the 3 mil balloon, we came down to 111 seconds, and then on a 7 mil balloon, we came down to 120 seconds, which is dramatic difference. On the next chart below, we see it in percentage, which brings us down to almost 60%. So this is definitely a positive feedback, which we got directly from the market. And thanks again, Ray, for letting us share this result. And the other customer, unfortunately, I can't share the name because it is also a very big client. But thanks also that you were doing some tests for us. And here we see kind of a bit of a different layout of tests. We see 7 different steps where he improved the system with a new rapid heating block, a new tooling. So we can see each test run, the time came down dramatically, and we came down to 95%, which is wonderful. 59%, sorry. And yeah, again, a very good result, and gives us confidence that this makes a big difference for our customers. And once again, thanks to these 2 customers for letting us share the results with our broader customer base.
Thank you, Josiah. So we see that with the reduction of the heat up time, we have an overall reduction of the whole process time. What are some more benefits, Josiah, for our customers when they use the new heating block system, the rapid heating block?
Yeah, sure. Obviously, overall, we have a shorter cycle time. That was on the goal of the project, and we're happy that we are able to prove these results. In addition to this, we want to show that we have a system that's backward compatible to our existing machine base. So basically, the current machines which you can buy from us, which we show also on our webpage, are able to accommodate these new rapid heating blocks. And this is a great benefit, and also has impact on your cost if you want to do improvement on your cycle time. And you also have the option, you could only change the rapid heating blocks and use your existing tooling, or you can also turn it around and say you just improve your tooling and you use your existing heating blocks. So either way would already give you some improvements, but sure enough, we would recommend to do the full change and improve everything in one step. Yeah, this, I would say, are great improvements, yeah, for our customers.
Absolutely, thank you, Josiah. And so again, the system is backwards compatible. So from the 1800 machine upwards, you can use that rapid heating block system and benefit from that huge improvement and enhancement that we made on the system. So that means 1800 machine, 2550, 2530 4-up machine, and of course the 1555 room forming machine all can adapt to the new rapid heating block system. Just one question that came to my mind, Timon. I mean, we know that we have customers out there and say, okay, I just want to use the heating block. I'm going to go with the new heating block system. Can I rework the current heating blocks to the new system, or do I have to buy the new ones?
No, you can't, because I mean, we really worked on the core of the system. So if you would do that, we really kind of leave most of it behind, and so I think it makes totally sense to buy new.
Absolutely. One more question that came in through the audience is, what is the material for the balloon molds that we are using? You want to answer it?
Yeah, so traditionally we're using Kufin, and what you've heard here is employed 9440. You actually can find material already on our balloon for mold configurator on the web page. So it's a material with a lot of copper inside, which makes it also a little bit more expensive, but it's very powerful. So if you look at the thermal diffusivity, which is kind of the key number if it comes to the heat up, which is the ratio between how much heat is actually needed to heat up the material itself and the conductivity, we really have a very good number there, even better than traditional other materials like copper beryllium, which is also good, but not as good as alcohol.
Yeah, thank you so much. So you can see, dear customer, we share those information. We want to be open about it because we know that some customers, they have the capability to do their own molds. Of course, BW-TEC offers that capability, and I believe it takes expertise to really make a good quality mold, which of course has an influence of a good quality balloon at the end. You mentioned the heat distribution. That leads us to the next topic, to the next block that we want to talk about. How does the new rapid heating block system affects the heat distribution and uniformity of the mold, which of course causes an increase or has an effect on the quality of the balloon itself. Timo, thank you.
Yes, so now we're talking mostly about longer heating blocks, because in the short heating blocks, heat is distributed very quickly. So let's say below 120, 150 millimeters, it's not really an issue. But what you can see here is actually a temperature probe insert for a 250 millimeter balloon mold. So now it's actually this guy over here sitting on our table. And what we do for many different lengths, but also for this one, we insert a probe with 5 different PT100s sitting here, and we insert it into the heating block, and we heat up to 155 degrees, which is now a little bit higher than what you expect in a traditional process, but we do it on purpose because as many of you know, heat transfer and heat flow is actually proportional to the temperature difference you see between the heating element and the surrounding. So if we heat up higher than our actual process, everything is going to be more pronounced. We have more heat flow, we have more losses, so we can see the differences between individual systems much more clearer. So the results we're going to share are therefore implies that on the process itself, the differences will be smaller. And just to get it clear, but this is kind of a very good way to get into the differences between different systems. So this is now a measurement of a 250 millimeter times 14.3 heating block. You see that time on the x-axis, and on the y you see the temperature again. And the green lines are the temperature of the heating block itself, and the red and orange lines are these 5 temperature measurements. The blue line is actually the range of these 5 temperatures. So we are looking always what is the maximum at the current time and what is the minimum, and this gives you this blue line. So this is you can see that you have quite a while, so over 200 seconds until you reach somehow a steady state, and then you come to 8 degrees approximately of the range of temperatures you see in steady state at 155 degrees C, which is not bad. But if you compare now to the rapid heating block, it's a different story. Now I have to say here, this data is a little bit preliminary, because then in the first step, we looked mainly on the temperature distribution and not so much on the speed. We're actually currently working on the speed now, because we can also improve the speed by working on the heating cartridges. But this is, we're not going to be versed in that one. So what you see here now on the rapid heating block, we reach steady state much faster, and we come down to 2 to 3 degrees in range. So this is very, very good in steady state, I think. And what we're going to do now to get a feeling of the spatial distribution, so how is the temperature evolving over the length of the heating block, we make slices in this graph and look at certain times how are our 5 different probes actually doing. So you see on the x-axis the sensor position and the temperature range. We start at the attack time, where the temperature is first seeing a change. We have 30 seconds, 60 seconds, 90 seconds until we reach steady state right before we start cooling. So the blue is actually the steady state profile. Now this type of heating block is a dual control one, and the one of you who are very good familiar with our portfolio, we actually offer two kind of heating blocks already. The dual control, you have heating cartridges from both sides of the heating block, and you're getting a short unheated zone in the center, and that's what you actually see in this V shape, because the center of the heating block is actually seeing quite a big delay, because it's not heated directly there. So it has to wait until the heat is flowing from the side. But this helps in the steady state profile. You can see this is now beautifully flat in the center. We also have single controlled heating blocks already, where we have one cartridge over the whole length, which performs better in terms of heat up. So there you see a very smooth profile when you're heating up the system. However, in steady state, these systems tend to perform worse. So we have a more pronounced Gaussian distribution of the heat, of the temperature, sorry, in steady state. So let's have a look on the rapid heating block. So this is kind of, we still see not a perfect distribution during heat up, but surely much better than what we see here. And we see this very, very flat, very smooth distribution in steady state, which, as the graph has shown before, is like 2 to 3 degrees at 155 degrees Celsius and in steady state conditions.
I think this is obviously for a customer great news, because we all know it's not just about speed, it's also about stability. We need a stable heat profile in order to have a consistent wall thickness on our balloons. So I see this as a huge side improvement from this project. And we all know if the wall is more stable, we have a better yield in our production, and for that we have a high productivity. So another great benefit for our customers. And last but not least, I also see it in the R&D phase that we have an improvement when we know how accurate and how even our heat distribution is, especially on a long balloon, or also maybe on a product that's not balloon related, which may produce in a long heating block. So again, this is a great improvement. And I said it's like, from now on, it's like making Swiss chocolate. You just know it's going to have good results when you use the system.
Yeah, thank you, Josiah. We certainly will have some chocolate after the webinar here, hopefully you as well. So Timon, just in short, tell me, on the old heating system, or on the conventional heating block system, we had a temperature delta on a long heating block of what, and on the new rapid heating block system, what's the delta going to be like?
So on the traditional one, we see 8 degrees in steady state at very high temperatures. So if you go to lower temperatures, it will be less, maybe 6, maybe 7 degrees, but still measurable. And on the new rapid heating block, we go below 2 degrees. I'm confident that if you only heat up to, let's say, 130 degrees, you will see like 2 degrees or less over the whole length of 250 millimeters.
Thank you. I guess just in summary, the rapid heating block system, the new concept that we have here, brings 2 main benefits for our customer. One thing is time reduction, improved timing, improved process time. That's huge. That's one thing. The other thing is that we have just more quality on the system, because we could reduce the delta. The heat uniformity is way better than before. That means, in a summary, we increase quality and we increase quantity with the new rapid heating block system. And again, it's up in the market. You can use it on the older system. You can only use the heating blocks, or only use the new mold material, or you can combine it to get the maximum effect that we can provide for you. That means a reduction of the heat up time by 50%, and as we mentioned before, a heat distribution by 2 degrees over the whole length of the heating block.